Okay, so from now on, we have to start all the Excel presentations with this slide. So I guess if you don't want to be recorded, you'll have to leave. I guess those looking on remotely can push some button to shut that off. But so anyway. Okay, so today I want to present some information on time series analysis. And time series is probably a statistical method that you may not have seen. It's pretty uncommon in the medical literature. In fact, I can't even remember seeing any time series analysis in any medical literature I've seen over the years. But there are some interesting applications of it, and that's sort of what I like to talk about. So I'm going to present this in the context of data that we have from the Bridges program, in particular looking at 30-day readmission rates. So time series analysis is really kind of different from other analyses that we're more familiar with, like linear regression or logistic regression. And one of the things about time series that you have to understand is that the times of observation occur at regular intervals. In other words, you have to have, like monthly intervals or quarterly or yearly or whatever, okay? Whereas in some, epidemiological kinds of analyses, they don't have to necessarily occur at the same time. Actually, so you can kind of make your data fit that however you want. So, for example, we might have, in the case that the example I'm going to give, we have monthly 30-day readmission rates after hospitalization. So mostly where you find time series analysis is in the field of econometrics. In fact, all the seminars or classes that I've been to on time series has been taught by an economist. I mean, he's well versed in statistics, obviously, but and so the method I'm going to talk about is referred to as the Box-Jenkins method. It goes back a number of years, but it's probably the most common time series analysis. So here's probably arguably the most famous time series in the world. Everybody probably has seen the New York Stock Exchange, and this is basically what a time series is. It's observations at a particular time point. I'm not sure how they do that. I guess they could do it by the minute or hour or day at whatever time period they want to look at. But that's what a time series looks like. So one of the main things is that, actually the main thing about time series analysis is that the value of the observation or the mean or whatever you're looking at a particular time is a function of past values. And in the time series jargon, these are referred to as shocks or innovations. But I won't use that term because I'm so unfamiliar. But that's really what time series is about, is that past values predict future values. So to understand that, then we need to then understand the concept of lags in time series. So you have our time points, time, I just lay on time 1, 2, 3, 4, 5, and so on. So when we talk about lagging the time series, lag 1 is then correlating time 1 with time 2 with time 3, 3 with 4, 5 with 4, and so on, okay? The second lag then is correlating time 1 with time 3, time 2 with time 4, and you can go through the whole time series this way. And so you get a correlation between the pairs and the different lags. And this is the correlation between time points is, in time series is referred to as serial correlation or autocorrelation. Okay, and the basic principle or fact here is that that observations closer in time are more highly correlated than observations further apart in time. So, like, we would expect the observations at times 1 and 2 to be more highly correlated than, say, at times 1 and 5 or 2 and 5. Okay. And so, given this, if you were to plot these correlations over all the lags that you could construct for your time series, this is what it would look like. So the correlations will be high when they're close together, and then they will die out, and then when you get back to time 10 with time 11, then they start to increase again. So you get this periodic kind of graph when you look at the correlations of the lags. Okay. If you want to ask any questions, go ahead. This is supposed to be informal, although we're spread apart here. But
why does it come back? Why do you say, I understand the correlation in the earliest?
Well, so when you get out and you're correlating, say, lag 20 with lag 21, that should be fairly high. So that'll have a high correlation further out in your correlation of lags. Okay. So there are several components of time series that we need to understand. One is trend, okay? And that's fairly straightforward. That's just like in regular linear regression, you think of a slope. So, the series might be trending up or it might be trending down. So, like a stock market crash is most, again, famous example, or going way out. Then we have what's called a cycle. So the series might be, oscillating sort of like sine waves, but it's aperiodic in the sense that it's not. It happens at different times, and in the cycles are, at different lengths. They have to be closer together, further apart. Seasonality is basically a cycle that's periodic. In other words, it happens on a regular basis at the same time throughout your series. And then finally, random noise, which is analogous to error variance in regular regression. So here's an example to show you what seasonality is. So in the upper left there is, I think that's flu outbreaks, or maybe something else. I can't read it, and then I have a graph from the CDC of flu, pneumonia and flu outbreaks, and you can see the seasonality that, just as you would expect, that it occurs on a periodic kind of basis, and those periods have essentially the same length, like they occur in the wintertime, basically. So that's what seasonality refers to. Okay? So then what we want to do in creating a model of the time series, we want to smooth it. In other words, we want to, the time series bounces all around, so we want to get some function that represents that. And so what we're going to do is we're going to smooth the time series. So there's different ways that you can do that. I've just listed a couple here. The most common one that we use is what's called a moving average. And moving average is just that. So if you have, say, a 3-period moving average, what that means is you add up the values at time 1, time 2, and time 3, and divide by 3. And that's your first point in the time series. Then your next point is time 2 plus time 3 plus time 4, and you divide by 3. And so what you're doing when you do that is you smooth out your time series. And you can see that the more points you take, the smoother it's going to get. In fact, you can take so many points that you basically get a horizontal line. That's what moving average is. And then there's just common regression, linear regression. that we could use. So here's a couple of examples of my monthly readmission rates. So the line that bounces up and down, has highs and lows, that's the observed. So the first one, I smoothed it out with what we call a locally weighted least squares regression. And you can see that really smooths it out. In fact, it's probably so smooth that it's not too informative. But the bottom one is a nonlinear smoother, and you can see that it's more smooth than the original series, but it's a more jagged than the regression smooth line. And you can see that you get kind of different pictures here. So if you over smooth something, you might get that kind of representation there where it looks like it's going up, whereas here the nonlinear one actually captures the peak here and then the drop. So that's one of the things in smoothing or in doing time series analysis. You have to sort of figure out which is the best smoothing to use. Okay, so now we're going to build a time series model. And in time series, the model is called an autoregressive moving average model, or ARIMA. And if we have a time series, it has to be what we call stationary before we can estimate our model. And there's kind of technical definition of what that means. I'll show you in pictures, which will make it a little more clear. But if our time series, observed time series, is not stationary, then we have to do something to make it stationary before we can actually build the model. And so what is often done is to difference the time series. And so then we would have an ARIMA model, or an autoregressive integrated moving average model. And what differencing means is that you just subtract the value at a given time with its with the next value. Take time t and subtract the time before from it. Okay, and that takes out trends and cycles, sort of things. Okay, so the two most important components that we're going to have in our model, though, are the autoregressive correlation between time points, and then the smoothing with the moving average. Okay.
So, Paul, essentially what you're saying is that before you can run the time series model, you did all the leads and lags analysis and took that information out of the model. Is that what stationarity means? You've accounted for that in your model.
Yes. Okay. So here's a picture of what I'm talking about. So here's a time series that obviously has trends to it, and obviously it's not stationary. So what we would have to do here, in addition to including autoregressive components and moving average, we probably are going to have to difference it. And so when we do that, then we get something that looks like that. And so your stationary time series will have a mean of 0 with a finite standard deviation. Okay.
So what happens when that variation of the time, the relationship to time, is meaningful? You essentially lose that information, or can you still?
No. Yeah, right. I know it doesn't. In terms of what we do in regular regression, logistic regression, linear regression, that's why I say it's really a different kind of analysis. Okay, but when you build the model, this is what you use to build the model. But it's going to capture all the things that you want to see in it. Okay. Okay. So we'll get to the good stuff now. That's kind of the introduction. That's theoretical stuff of what we're doing when we do time series analysis. Okay. So as I mentioned before, in medicine, you rarely see time series as it's typically used. But there are a couple of applications of it that make sense in some contexts. And One is what we call an interrupted time series. And so the Bridges program kind of really fits that, because what that means is that you have a time series, and at some point in the time series, there's something that happens, an intervention, an implementation of some, something, some program. And what you want to know is, did your intervention in any way change the time series? Did it cause something to happen different than happened before? Okay. So that's primarily what we're going to look at, and then I'm going to touch on another sort of really fascinating application of time series, and that's what's called Granger causality. But I'll get to that at the end. Okay, so here's the data I'm going to analyze. This is monthly 30-day readmission rates from January of 2010 through July of 2014 at Christiana Care. Okay. And so what I've done is just taken all the patients who were readmitted in that particular month and got an average for each month. Okay, so that's the data.
And so that's a percentage? Each of those?
That's a number. That's an average number. Oh no, right, okay. Yes, it's a percent. All right, that's what it would be. I'm sorry, it's not a number, it's a percent. Yes, you're right.
So in January 10, there is a 3.5% readmission? Is it?
Yes. According to Christiana base. Okay. So if you plot that, this is what it looks like. Okay. So now in building our model and doing our analysis here, this is kind of the first thing we want to do. We want to look at our data, in particular our plot. So what does this plot tell us? Is there a trend? Is there seasonality? Is there a cycle?
I don't know.
Cycle. I mean, there seems to be some cycle.
Well, yes, but I could make
random noise.
I could make the argument that this is just random noise about a mean. It's just, because look, it's just bouncing up and down. Okay. Well, let me give you a little clue here. It's really hard to see a trend in this, but look at what happens every summer. Everyone see that? Looks like it drops every summer. Okay. Or at least during 1 month of the summer. Okay. So there's a possibility that we might have seasonality. Okay.
So it goes up every January too.
Yes. Right, but that would be a cyclical kind of. Okay. So what I want to then first do is I want to say, okay, can I just analyze the series as is? Because if I can, that solves a lot of problems, because then I can just apply regular regression to it. Okay. So what I have to test for is my time series just, white noise like the one I showed of the IBM stocks. It has a mean of 0. Well, there's a number of tests you can do, and this is one of them. And basically the bottom line here is that the test statistic is significant. So that means that no, it's not just white noise. It's, there's, I have to do something to eliminate that. There's, trend, there's seasonality, there's cycles, whatever. Okay. So then I'm going to look at my autocorrelations over the lags. So I don't have the really pretty one that I showed before because I don't have that many time points. But you can sort of see where you get kind of that sine kind of wave in there. except that the correlations aren't that big. And you can draw a confidence interval, although I don't really pay too much attention to the confidence interval. But so because the correlations are not terribly large, then that tells me that, well, maybe I don't have to worry about autocorrelation. Maybe they're not that correlated from one observation to the next.
So what is large or not large? What's the definition of large correlation?
Well, typically what is done is you look at those that are outside the confidence limits as being.
And so the dotted lines are the confidence limits?
Yes. And here they're really wide. And they're really wide because I have only 50 some time points. Okay. So then what I do is I, with that information, build my model or put in what I think. So what I've done here is, first of all, because each month has a different number of observations that the readmission rate is based on, I'm going to weight the analysis by that number because it varies from month to month. Okay? Now, if I have thousands of patients at each month, then I probably don't need to worry about that. So my first model that I'm going to look at that I think is the model, you can see there is a 101. So what that means is there's an autocorrelation. I'm not differencing it. There's moving average, and then I'm taking into account the seasonality that I thought I saw, and what at the end of that, the 12 means I'm looking at as a yearly, as a 12-month interval.
So you had to specify where you saw this.
Yeah. Which obviously now what I'm doing is I'm kind of guessing, okay, based on what I saw. Okay.
Can you repeat again what's the 101 here?
Okay. The first number in the model refers to the autocorrelation. So putting my 1 there means that I'm.
You mean after the word ARIMA?
Yes. And ARIMA, yeah.
ARIMA. All right.
They're both the same. Okay. So right. So the first one refers to the autocorrelation. So I'm assuming that I have a first autocorrelation in my data, in my time series. Then the second number refers to whether or not you differenced your series. Okay. So in this case, I haven't differenced it yet because I'm hoping I don't have to do that because it makes things a lot easier. The third number, the last number there, is then the moving average. Okay. And then I'll show you another one in a minute here, and then I'm putting in what I think I saw as far as the trend goes.
So why is the moving average 1? What does it mean, 1?
Well, that's a first order.
Oh.
Yeah. In other words, you do it once. The second order would mean I do it twice, so on. Okay. Okay. So some interesting things happen when I do this. So the first number I have here that's labeled a constant, that's the mean of the time series. Okay. So the mean of that entire time series is 7.6. Okay. And then I have coefficients for my autoregression and coefficients for my moving average. And so I can see that, as I kind of expected, that the autocorrelation is pretty small, 0.008. So I can maybe ignore that in the model. Okay.
Where is 0.008?
That's all bigger I can make it. Otherwise, okay. And then and that's not statistically significant. And then the moving average coefficient, and then I have the same thing for my seasonal, 12-month seasonal coefficients, the autoregressive coefficient and the moving average coefficient. Okay. So now my question is, okay, is that the best model? So are there other models that might do just as well? And so that's kind of well, to me, it's kind of one of the interesting things, or one of the things I kind of like about time series. You can kind of pick your models. So here's another model that ignores a seasonality component. And so there are my coefficients. Again, the first one being the mean of the time series and so on. And this is a model with auto-regression and a moving average, but not the seasonality. So I do that model.
Oh, can you go back to
this one or the one before?
So you change the estimate of the moving average of the ARIMA model by having the seasonality of that model. Absolutely.
Which one?
The moving average under your
Right.
the first model is 0.23, so it didn't really change that.
Right. But it did change the autoregressive one. Okay. Yeah, good observation. Okay. So then I do a model where I have only the moving average component. I've taken out the autocorrelation. And those are my coefficients for the moving average and the constant, the mean. And then I do another one where I just include the autocorrelation coefficient, but not the moving average. Okay. Now, there's a way of checking which one of these models is better than the other, and that's using what we call information criteria. I'm not going to go into that, how you calculate that, but it's commonly used in almost every method for building prediction models. And there's two kinds, the AIC and the CIC. I've always wondered how do you pronounce that. I think it's Hikes and Bayesian AIC. And for the information criteria, smaller is better. Okay, so you can see with all the models that I did here that the one that had actually either one that had the seasonality in it is far better than the other ones that didn't. So I need that obviously in my model. And here, whether I include the autoregressive component or not doesn't make that much difference. I could include it or not, but I left it out. Okay. So here's what my model then looks like with no autocorrelation, moving average, and then I didn't put it there, but then it's seasonally, the seasonality is in there. So there's my original, and then that's what the my model looks like. Okay, so you can see that basically what it does is it sort of smooths it out, but you still have, some variation in there. So now what I want to know is, okay.
So it looks like the seasonal variation looks to be smaller.
What?
It looks the model seasonal variation looks smaller than the observed seasonal variation.
Yeah.
Is that what happens when you put it in the model, or it sort of takes it out?
Yeah.
To some extent.
Yeah, I mean it's still there, but it's not as obvious as it is in the observed.
So basically, you control for the seasonal variation.
Yeah.
Kind of.
Right.
Right. Okay. So now I need to find out, is this model stationary? And so I want to test that. And my test statistic says that it is, or I can claim that it's stationary because it's not significant. So that means that I can get by without difference in it, which is kind of nice. Okay. So now I've built my time series model, and so now what I want to do is I want to find out, did my intervention change anything in the predicted model? in the time series model. So now what I'm going to do is I'm going to add another, I guess before I do that, there's ways that you can figure out what the change looks like. So, these are kind of the combinations of the change that you can get in a time series. I'm not gonna, that's a little more complicated to analyze those. I'm not gonna do it. I'm just going to put in a variable to see whether there was a change or not, okay? And so what I'm doing is I'm going to put in an indicator variable that is 0 before April of 2013 and it's 1 after. And so what we're saying is that this is the start of our bridges intervention, and so we're going to see if the series changes after that intervention. Now there's some discussion within the analytic bridges, within the bridges analytic team, where that intervention should start, but we'll just do it here for now. Well, actually, that's sort of important because that's kind of typical of intervention you do, or most interventions you do. It's like there's never really a hard and fast start and stop kind of thing to it. You have some program you want to implement, and it takes a while for that to happen, and things might be changing while you're implementing it, before it's fully implemented. So you might see some change, before that. But anyway, so that's what I'm going to test. And so I'm going to put in another variable, my bridges indicator in the model, and I'm going to see what happens. And so fascinatingly enough, it tells me that the bridges intervention has a negative 0.5 impact on the mean, and that is statistically significant. So what that means is that I reduced, after the intervention, I reduced the readmission rate by 0.5%. So, there you are. Now, I know some of you might be skeptical of that, but
basic scientists I know who would say, now it's time to quit.
And I have in my model all the model that I built, all the other things, the moving average, and then the seasonality. So that's what interrupted time series is about, and it's kind of, I think, a neat way of looking at interventions, implementations where you have data over a fairly lengthy period of time. Obviously, if you do just a before and after, you have one measurement before and one measurement after, then that's not time series. But so okay, so let me in the few remaining minutes here talk about Granger causality.
Before you go on, can you go back to the slide?
Okay, yeah.
So there's nothing in here. We talked about trend before. The trend's out of this, but this output here doesn't give you any sense of a baseline trend. There's nothing I can take from that, right? Because the moving average is not trend; it's different. So,
well, no. What you can take out of this is the mean of my series is about 7.77.
Right, but I mean, if it was a slope or a trend prior that you've taken out.
Oh, right, yes.
We're not accounting for that anywhere here. We have to add other cut points or something that we thought we saw.
Yes, that would be related to what the change looks like. If you wanted to see if it's a gradual change and then you lose all your.
So it's not like linear regression would give you the slope of this line prior and then you see there's nothing like that in here.
No.
Okay.
Not in this one.
Not in this one.
This is just yes or no, 0, 1. Okay. So Granger causality. So basically the question here is, does one time series cause another? And what we mean by cause is do past values of one series help predict values of the other series. Okay? So we're using the lags, again, to test that. And this is known as Granger causality. Now, Granger causality is not causality in the epidemiological sense of the word or how that's used in science. But it does kind of get at one element of that, and that is in causality. If you have true causality, then the cause has to precede the effect. So what we want to look at when we do Granger causality tests is basically we're going to do two tests. We're going to test if y is a function of x, and then we're going to test whether x is a function of y. And let's say that the time series y is the one that we think should be caused by x. So then if it turns out that the test for y as a function of x is significant, and x is not a function, is not significant in terms of being a function of y, then we can say that x causes y. However, if it's not significant in the direction we want and it's significant in the other direction, then we can't. We have to reject the fact that x causes y. If both of them are significant, then we're in really quandary because we really don't know. We really don't have anything. We don't know what's going on. And then obviously if they're both non-significant, then we can conclude that they're not at all correlated. So I want to look at just a couple things here. And one is whether comorbidities cause Granger cause readmission. Okay. And from a typical regression or from a usual regression standpoint, what we would look at is, is that a predictor? Is comorbidities a predictor of readmission? Okay. So this is the plot of both series. And so what I'm going to test is whether.
So what is the Granger comorbidity? Is that the number of? Oh, it's the comorbidity
No,
count.
this is the comorbidity count on this axis. You got two axes here, okay? They got two time series in different scales. So here's the comorbidity axis over here, which is
So it makes it look like our patients are getting less sick?
it's sort of, well, yeah, it kind of looks like that.
Wow. This variable is under revised construction.
Right. That may change after we. Okay,
So,
but
I think that the number of comorbidities may go down as people get sicker because you may code differently. You can get something really perverse. For instance, you see hypertension tends to be coded in people who are less sick than people who are sick. So that absence of hypertension tends to predict bad outcome in administrative data sets, which is nonsense.
Yeah.
Same thing happens with obesity.
Right. But so anyway, so I'm going to look at whether the relationship here, whether the comorbidities cause readmission or readmission causes comorbidities. And another one I could look at is congestive heart failure, same sort of thing. So there's just a plot of the two series. And so when I do my test, what I'm interested in then is what is in my output here. Readmission is a function of CHF, readmission is a function of comorbidity, so on. So that's what I'm primarily interested in. Is that relationship statistically significant? And you can see that, except for previous hospitalization, they are. And then the all means that all three of those are in the model at the same time. Okay? So, so when I look at that, I say, oh boy, it supports my hypothesis. Well, not quite, because I have to then look at the other key test here. Is CHS a function of readmission? Is comorbidity a function of readmission? And is previous hospitalization a function of readmission? Unfortunately, they turn out to be not significant. So I can then say that CHF and comorbidity Granger cause readmission, which of course I know that when I did my logistic regression because they're significant predictors of
But I think that previous hospitalizations also was a strong predictor of readmission. Isn't it what you found? In that previous hospitalizations?
Yeah. Remember, I'm doing something pretty different than I do when I just do
Logistic regression.
Oh, this is looking back a step, like this is some kind of, this is an assessment of the lag.
Right.
Right, which is interesting, right? Because the way that the data set is structured here, the person who has the comorbidity that would contribute to the comorbidity burden in that population and that person's readmission are coded in the same time interval. Right? It would be strange to see a month before the rate of CHF increase and then readmission increase for patients admitted the next month. So I mean, there's some logic there that doesn't necessarily make sense.
Yes. Okay. All right. So let me just.
Is this a one-time lag?
What?
Was it a one-time lag? Was the question from?
A one-time lag of. What was the question
Granger
again?
causality test. Was it a one-time lag?
No, there are two lags.
Where is that indicated in the output?
That's not part of the output I showed, but you do get that output of how many.
So how did you select that? How did you select two lags then?
Because that's sort of the minimum that you can do. And I mean, you could put in whatever you want, and get, different answers. Hopefully they'd be sort of similar, but the, two is just, what I put in, which is sort of more or less arbitrary.
Thank you.
Okay, so to sum up then, time series, I think, can be used as it would be a good, method, a tool for using when we have an intervention and you have data in some length before and after that. One thing about time series analysis that's really a big part of it that I didn't go into is forecasting. Now, obviously, in economists, that's what they want to do. They want to forecast what's going to happen in the future. I don't really see that.
Well, they're never right.
Right, yeah, it's like, what difference does it make? But, and they're doing that to try and make money. So, but anyway, I don't really see that as much of much use in medical research predicting from time series, because first of all, you're not predicting for an individual patient, you're predicting some sort of trend. And then if you want to assess the relationship between two or more time series, might be something would be useful in medical research. So with that, I will stop. And if there's any more questions, entertain those, or otherwise, thanks for your time. Yeah.
Question. I mean, I think there's a huge use for this in infection control because frequently, we have long-standing trend data for infection rates, and then, multiple different times that different interventions went into effect. And I guess my question was, when you have multiple interventions, some of which can happen kind of right then, like the lab switches to a new test, and that, that's like one day and it's switched. But other things, like we start a new hand hygiene program, that takes time and may or may not get like full penetrance into the system. Can you adjust, and then the different interventions may interact with each other. Sure. And you may be like, once you get to a critical bundle, that's when you start to see an effect. Can you adjust for all those?
Sure, you can. I mean, I just did it here where you have one intervention, but you can put, more than one time point in there. But you look at the series, you build your model, from the series as a whole, and then, look at the interventions And you can look at those, and I mean, you can look at each one individually, or you could look, at, say there's one main one, and then something else happens, and then you want to look at it, after those two have happened, So yeah, you could.
And can you adjust for, like, you might have a start date for a certain program, but then it may
Right.
take months for that to actually be fully implemented. You can adjust.
Well, that's the same as bridges. It's like, it takes a while to implement that. So in reality, maybe our starting point is really, January of this year rather than, last year or some other date, later on.
You just
But
move the date. You just move the date of the intervention.
But that's a decision the researcher would make.
I have a question from UD.
Yeah.
I'm sorry, I can wait.
No, that's okay. Go ahead.
Okay. There's a little bit of a time lag in the microphone, but with the interrupted time series analysis that you showed with the bridges intervention, in an ideal world, wouldn't you want an approximately equal number of time points after the intervention as before? Because the trend could go back.
Yes, that would be ideal, and that's I didn't mention that, but that's sort of one of the things why I didn't really go any further than just putting in bridges as an indicator variable, because we really don't have enough data after bridges, whenever that started, to really say much of anything. But yeah, you're right. You would like to have a fairly lengthy series that's somewhat equal to what the series before was.
Thank you.
Okay.
Okay.
Thank you.
That's terrific. Thank you.